Hello everyone, welcome back to MAT052. Hope your week is going well. Today we're going to start talking about the central limit theorem, and mixed in with chapter 6 normal distributions, there's going to be times that we're going to have to either use the straight normal distribution, here's a number x and I want to find the probability of less than. And then in other problems, and it's very sneaky, it'll say what's the probability that I take a sample and the mean of the sample is less than a number. Okay, so it won't be an individual, it'll be the mean. And that is what the central limit theorem tells us. And this is what this little worksheet is about, is identifying when can I apply the central limit theorem. Okay, so the central limit theorem basically says that if it meets conditions, then the population and the sample means are related. So if I took a bunch of samples and if I did all of those sample means and then I averaged those, so I've got a bunch of samples, I found the mean of each one of these samples and then I averaged those, this would be related if I took all of those, would just be the mean of the population. So the mean of the sample means, that's how you read that, the mean of all those sample means, if I took all the possible, and this is for a particular value, okay? So I couldn't just do just a bunch of different sizes. I would have to have some fixed size of the samples. Let's say 30. That's a good number, and we'll see why. But this has to be, if we took just a bunch of samples of size 30 and started calculating the mean of those means, for each one I had a mean, and then I averaged those, it turns out that they're related to the population mean. Okay. Also, if I took the standard deviations of all of these things, so if I took the standard deviations of all the x bars, it turns out to be sigma over the square root of n, where n is that sample size again. Okay. So the standard deviation of those means. Okay, so let's kind of go through here and you'll pick out what conditions can we use these things about the population. So recall from statistics class that a sampling distribution is created when we take repeated samples of the same size. This is whatever the same size is n. So that sampling distribution is going to look a little differently for each n size. But what we're going to do is consider that we're just taking a particular size and then just focusing in on that, because this is where that'll come into play. Okay. Each sample includes a set of randomly chosen members of the population. Each sample. Okay. So I'm grabbing one sample, but what I'm saying is that if I did this for all of the possibilities, these are related. Okay. So this is done with replacement. We have to be careful that we don't have a small enough population that when we do a random sample, that it would be problematic. We need to be done with replacement so it's independent. So it is possible that the same member of the population can be chosen in more than one sample, although unlikely with a large population size. Okay, so if it was small enough, I can't do it without replacement. Okay. Here. So we can study a sampling distribution to get information about the original distribution. The central limit theorem, CLT, the CLT tells us that we can treat the sampling distribution as a normal distribution. So what happens is that once I take a number of those samples of the fixed size, and if I continue taking these things, and then if I started graphing these things out, it turns to be normal. So each one of these, this would be like an x bar 1, x bar 2, x bar 2. All of these things would create a sampling distribution, and it would be normal if these conditions, at least one of the two conditions are true. So the sample size for each sample in the sampling distribution is greater than 30. So if n is greater than 30, I'm good. Okay, so this would be, the sampling distribution would be approximately normal. Okay, we can treat it as a normal distribution. If the original population is already normally distributed, regardless of sample size and the sampling distribution, I would turn out to be this. And this would work no matter what the size. Okay, but as long as the population is already normally distributed. So I'm going to look for one of these two words or both. It's okay. I can be normally distributed and greater than 30, I'm good, but it didn't have to be as long as it's normally distributed. If I don't see normally distributed in the statement of the problem, I cannot treat it as normally distributed unless this thing is 30. If it's not big, I can't do what we need to be able to do. Okay? So in both cases, the CLT tells us that the sampling distribution will be normal. The mean of the means will be mu, and the sigma x, the standard deviation of those x bars, are related to the population standard deviation divided by the square root of n. So this is what the CLT can work for us. Okay, this we'll be able to know, and then we can ask probability questions about the sample mean. What would be the probability that the sample mean was between two numbers, less than, greater than, those type situations. But here we would use these two numbers to calculate the probability. What would be the z-score? It would be your particular x bar minus the mean of the x bars all over the sigma x bars. So if we know the population, this is usually given, and then we can basically go to that. Okay. So, but what we want to do in this worksheet is focus on when can I use this information to start building things, probabilities about the samples. So the CEO explained why or why not you cannot use the central limit there. The CEO of a large company wants to analyze salaries for employees in her company. Definitely not normally, but she chooses 50 random employees. She wants to generate a sampling distribution with the results. Yes, you can use CLT, this information, but why? Because n is greater than 30. The size is not normally distributed. Now, if this was less than 30 in this case, with it not being normally distributed, she wouldn't be able to do it. It takes a large enough n greater than 30 for this to work out. Why or why not the CLT? Suppose that scores on a certain test are normally distributed. I like that word. Keith collects repeated samples of 5 students and uses those samples to create a sampling distribution. So this would be, for each one of these samples of 5, I created an average grade report and then used those to create those. So yes, I could use CLT results. And then why? I've got a normally distributed, these are normally distributed. So even though n is equal to 5, this is okay. Why not the CLT? A sampling distribution of average commute times is collected with a sampling distribution size of n equal to 12. Would that work? I see no information about the population being normally distributed. That's my big question mark. I have no reason to believe that it would be. I mean, just based on this, n is not, is it bigger than 30? No. So no. Can't use the central limit theorem results. Right? So go through these. That's what you're going to look for in each case. In each case, you are either looking for the words normally distributed and greater than 30. Okay? At least one must be true. Okay? I can't have a not normally distributed and n less than 30. But if I've got normally distributed, the size doesn't matter. This already shows up. So work on those. Go through, practice using, coming up as it normally distributed and greater than 30 to explain why you can use or cannot use the central limit there. Okay, so turn those in for me and we'll see you next time. Have a good week.